Hi folks, this is the second half of Module 5. We would have had a quiz today on elements 41 to 60, but we'll have that next week. Because of the storm, obviously we're not meeting. It's starting to pick up some wind out there. So I'm going to set my stopwatch for 10 minutes so I don't go over my YouTube time anymore. And then hopefully we'll be able to upload these videos as soon as possible. Okay, so today we're talking about an introduction to stoichiometry. We're talking about the concept of a mole. So a mole, as you know, we have words that represent certain numbers, such as a dozen. You all know that 1 dozen is equal to 12 of something, right? So if I said, oh, I need to buy 3 dozen donuts, you would easily be able to convert, right? If I said, let's see, I have 3 dozen donuts, how many donuts is that? We'll use D for donuts, so I don't have to write it. Then I want to cancel out dozen, so I'm going to say 12 donuts in 1 dozen. I cancel out dozen. 3 times 12 is 36 donuts. That's my answer. Just like there's 12 things in a dozen, we want to talk about today how many things are in a mole. 1 mole, and MOL is the abbreviation for mole. I'll write it out this time. If I write MOL, it's the exact same thing. 1 mole is 6.02 times 10 to the 23rd of something. So just like a dozen is 12 of something, a mole is 6.02 times 10 to the 23rd of something. This is an enormous number, unbelievably huge number. In fact, if you had a mole of soda cans, 6.02 times 10 to the 23rd soda cans, that would cover the whole surface of the entire Earth to 200 miles deep. So that's a huge number of soda cans. If you had a mole, 6.02 times 10 to the 23rd kernels of unpopped popcorn, it would cover the entire United States to 9 miles deep. If you had a computer that was even able to count 10 million atoms a second, 10 million atoms a second, which no computer we have can come close to, if it could count 10 million a second, it would take it 2 billion years to count a mole. 6.02 times 10 to the 23rd atoms, or anything. So this is such a huge number, we can't even imagine how big that is. But we call this Avogadro's number. You can read in your textbook about the scientist it's named for. I won't waste our little 10-minute clip on that you can read. But anyhow, a mole is 6.02 times 10 to the 23rd of something. You need to memorize that conversion factor. When you look at the periodic table, let's say you see boxes. Each element has its own box, and let's look at carbon, for example. Carbon has a 6 up here. 6 is the number of protons in every carbon nucleus. Every carbon that there is, every atom of carbon has 6 protons in the nucleus. It may have different numbers of neutrons. It might have 6 neutrons or 7 neutrons or 8 neutrons in the nucleus, but it'll always have 6 protons. That's what carbon is. But the number we're more interested in today is the bottom number under here. Now, this is a number that is an average atomic mass. 12.0 for carbon, but that's only to 3 significant figures. Other periodic tables that you might use in college will have more significant figures in the atomic mass. What that means is that 1 atom of carbon has a mass of 12.0 AMU. That stands for atomic mass units. Okay, but that has another meaning also. It also means that 1 mole of carbon atoms, so 6.02 times 10 to the 23rd atoms of carbon has a mass of 12.0 grams. So this is a factor that we know. 1 mole of something has a mass of the atomic mass in grams. So 1 atom, 12.0 AMU for carbon, atomic mass units. 1 mole of carbon will weigh 12 grams. So remember, we decomposed sugar last week, and we had that big mass of black stuff that was carbon. If I measured out 12 grams of that black stuff on the scale, I would know that I had 1 mole of carbon, or 6.02 times 10 to the 23rd atoms of carbon in that 12 grams. So that is the power of Avogadro's number, making us able to use the information on the periodic table to actually measure out a given number of atoms of something. And you do need to consider significant figures in this. Avogadro's number is an experimentally determined quantity. They use a technique called X-ray crystallography, which once again, lots of time ticking away. You can look that up, how that's done, but they can get to 8 significant figures on Avogadro's number. The lab we would have done today would have involved me making a very, very, very dilute solution of dish detergent, like a fraction of a drop would have been used of the dish detergent. And then we would have done that old experiment where you take a big bowl, cover the surface of the water in the bowl with pepper, put that tiny amount of dish soap, and see the pepper just all go from the middle. And the point of the lab today would have been to measure the diameter of the circle created where there isn't any pepper once the dish soap hits. And then we could measure the diameter of that circle. Then we'd know the number of molecules of sodium stearate, which is the ingredient in the dish soap that would break the surface tension and cause that zooming away of the pepper to happen. So we could actually measure how many molecules of sodium stearate are lined up across that diameter, and we could potentially take an experimental guess at what Avogadro's number is. And when we do it, we come, reasonably close for such a huge number. It's actually pretty amazing. So make sure you read Experiment 5.1 in the book. You've all seen pepper zoom away from dish soap on the surface of water. So you can figure out how that happens. And we just won't do that this week. Not my favorite lab, so it's okay. But it's very interesting. But X-ray crystallography gives us up to 8 significant figures on Avogadro's number. So it's a pretty secure figure when we use just 3, 6.02 times 10 to the 23rd atoms in a mole. Make sure that you do realize, though, that really is 3 significant figures, so you do have to round your answer to 3 significant figures unless one of your other pieces of data has fewer significant figures. Let's see. I'm at 8 minutes, so what to do? So if you look at a balanced chemical equation, let's look, say, at the formation reaction, like we looked at last week, of sodium chloride. A formation reaction, remember, just takes elements and forms a compound. And you have to remember that your homonuclear diatomics, of course, have to be considered. So we want to make sure we have a balanced chemical equation that satisfies the law of conservation of mass, and now we do. The coefficients that we have here are stoichiometric coefficients. Stoichiometry is the study of how different amounts of things happen in a balanced chemical equation. And Module 6, our next module, is all about stoichiometry. We'll talk a lot more about it, but this is just the first introduction to it. These stoichiometric coefficients, and you can see it doesn't appear to have one here, but it's really the number 1, right? If there's nothing there, it's a 1. So these help us to compare not just atoms. We could say we take 2 atoms of sodium and 1 molecule of chlorine, and we produce 2 molecules of sodium chloride, NaCl. And that is completely true, right? But what these also mean, the stoichiometric coefficients also mean that if you take 2 moles of sodium and react them with 1 mole of chlorine, then you produce 2 moles of sodium chloride. And that makes us able to use a balanced equation in the lab to figure out all kinds of great stuff, which I'll show you when we do our practice problems. So, balanced chemical equation tells us not just about numbers of atoms, but of numbers of moles. So that's huge information. Let's see. So I'm going to stop the tape. We're going to go over review questions and practice problems, and then hopefully we'll have short enough videos that it'll work on YouTube. So I'll be back in just a moment.